Hi, welcome to Hub. In this video, we are discussing the definition of maximum likelihood estimation and the optimal properties of the MLEs. So first, we will discuss about the MLE. What is the MLE? So this is the widely used methods for estimating the parameters of a statistical model in several or optimal properties that is make it a preferred choice in many applications. Now we will discuss the properties below. First is what is the definition? ML is a method of finding the parameters of any model, and it is widely used for finding the parameters. Right now, likelihood functions. So we have already discussed about the likelihood function in previous videos. So first we will find the likelihood function, then we will find the log likelihood function in this one, and now here we are discussing the optimal properties of the MLE. First property is consistency. Consistency says that when the sample size increases, automatically MLE converges in probability to the true value. Suppose that I have more samples, so my value will be correct, or my value will be converges to the probability to the true parameter value. In mathematically, we can say this sample statistics automatically tends to a true parameter when n is tends to infinity. It is called the consistency and ensures that the estimator becomes more accurate as data more corrected. Right. Now the second one is asymptotic anormality. This is also similar to the consistency, but in this one is also n is increases, the distribution MLE approaches a normal distribution, but in this one, the MLE is approaching a normal distribution with mean theta 0 and variance equal to the Kramer-Rao lower bound. So mathematically, we can say so root n theta cap minus theta 0 is tends to normal distribution where mean is 0 and variance is equal to the Kramer-Rao lower bound. This is Kramer-Rao lower bound. So this is called, and where I theta 0 is Fisher information, where I theta is the Fisher information and its reciprocal is called as Kramer-Rao lower bound. So it is allows for the construction of the confidence intervals and hypothesis tests. So this construction of confidence intervals and hypothesis test. The third one property is efficiency. MLE achieves the Kramer-Rao lower bound, meaning it has the smallest possible variance. It has smallest possible variance. It is called efficiency among all the unbiased. Suppose that we have lots of unbiased estimators in which there is only one smallest possible variance. It is called a efficient estimator. So variance of theta cap will be n I theta 0. This is actually a Fisher information, and this is a Kramer-Rao lower bound. And significance is ensures that the MLE is the most precise estimator of large samples. The fourth one property is invariance. Theta is the MLE of theta. Theta cap is the MLE of theta. Then for any function g theta, then MLE of g theta is g theta cap. So theta cap is MLE of theta. Now for any g theta, MLE will be is g theta cap, right? So if theta cap is the MLE of the variance of sigma square, then theta cap is the MLE of the standard deviation sigma. So theta cap is MLE of the variance, theta cap is the MLE of sigma square, right? So theta cap root will be the MLE of sigma. This is the property of invariance. Simplifies the estimation of transformed parameters, so we can transform the parameters accordingly. Now the sufficiency that is sufficient exists estimator for theta. MLE depends on the data only through this sufficient statistic. It is the reduces the dimensionality of the data without losing information about the parameter. So sufficiency says that if you have a lots of information about the parameters, so it is called the sufficient estimator. So actually MLE depends on the data only through his sufficient statistic. It is called the sufficiency. Now the next one is asymptotic unbiasedness. Asymptotic unbiasedness is called a theta cap is similar to the theta cap when n tends to infinity. For large samples, MLE is approximately unbiased, but it is not necessarily unbiased. It is not necessarily be unbiased. But in some cases, it can be unbiased, meaning its expected value equals to the true parameter value. That means that if n is tends to infinity, it automatically the expectation of the sample parameter will be equal to the true parameter value. And again, the next property is robustness to reparameterization. So definition is MLE is invariant under reparameterization of the model. If the model is reparameterized, the MLE of the new parameter can be obtained by transforming the original MLE. So this makes the method flexible and applicable to wide range of models. So MLE of the new parameter can be obtained by transforming the original MLE. Actually, we have discussed about this property, invariant property, in previous one. So we can transform the property by simply in this one, so invariance property. So robustness actually under reparameterization of the model. So this is can be transformed by the original MLE, and this method makes flexible and applicable to a wide range of models. Now the next, which is very useful in Kramer-Rao lower bound and Fisher information. Fisher information denotes by I theta, measures the amount of information that the sample provides about the parameter theta. It is defined as the I theta is equal to minus E del square upon del theta square log f x theta. This is called the Fisher information, and this is variance of theta which is always greater than or equal to the Fisher information, right? This is always so more information, less information, more variance, more information, less variance. So actually this is directly inversely proportional. So Fisher information says that we need a lot of amount of information for providing a better variance, or we can say less variance. So this is the property that we have discussed. Now right now we are discussing the limitations. And obviously in any method there is any, it can be limitations. So first is the sensitivity of the model assumptions. So first is saying that the sensitivity MLE relies heavily on the correctness of the assumed model. If the model is misspecified, the estimates may be biased or inconsistent. अगर मॉडल मिस स्पेसिफाइड है तो एस्टिमेट्स वो बायस हो सकते हैं या फिर इनकंसिस्टेंट हो सकते हैं. कंप्यूटेशनल कॉम्प्लेक्सिबिलिटी, कॉम्प्लेक्स मॉडल में मैक्सिमम लाइक्लीहुड में कैन बी कंप्यूटेशनल इंटेंसिव. तो देखिए कोई कोई मॉडल ऐसे होते हैं जो कॉम्प्लेक्स होते हैं, उनका लाइक्लीहुड निकालना पॉसिबल नहीं है, तो उस केस में ये पॉसिबल नहीं हो पाता. तीसरी बात ये है कि स्मॉल सैंपल बायस है, कि जो स्मॉल सैंपल्स होते हैं उसमें एमएलई बायस हो सकता है ना. लार्ज सैंपल में वो बायस नहीं होता है, दो दिस बायस डिमिनिशेस एज द सैंपल साइज ग्रोस. लेकिन जैसे जैसे सैंपल साइज बढ़ाया जाएगा ये बायस कम होता जाएगा. का मतलब है कि एक गंदी प्रॉपर्टी है, अनबायस नहीं होता, लेकिन अनबायस चाहिए तो आपको सैंपल साइज बढ़ाना पड़ेगा। तो हमने कई सारी प्रॉपर्टी पढ़ी, कंसिस्टेंसी, asymptotic efficiency, invariance, sufficiency, asymptotic unbiasedness और robustness। यहाँ पे कुछ एग्जांपल्स भी है, जैसे कि आपका नॉर्मल डिस्ट्रीब्यूशन दिया गया है n और म्यू एंड सिग्मा स्क्वायर, यानी कि मीन एंड वेरिएंस। सो MLE ऑफ म्यू इज म्यू कैप, यानी कि इसका मीन जो है इसका पैरामीटर होगा, है ना। यहाँ पे ये जो एस्टिमेटर है वो एक क्या है, कंसिस्टेंट है। क्यों? क्योंकि जैसे जैसे सैंपल का साइज बढ़ाते जाएंगे, इन्फिनिटी तक जाने जाता जाएगा, वैसे वैसे इस म्यू कैप की वैल्यू भी वो बढ़ती जाएगी और एक ट्रू वैल्यू तक पहुंचती जाएगी। दूसरा ये एक एफिशिएंट है, एफिशिएंट मतलब कि ये अचीव करता है CRLB। CRLB हमने पढ़ा था, क्या था कि वेरिएंस ऑफ थीटा कैप इज ग्रेटर देन इक्वल टू 1/n I थीटा। तीसरी बात है कि असिम्प्टोटिकली नॉर्मल है, यानी कि ये नॉर्मल डिस्ट्रीब्यूशन को अचीव करता है। मिलते हैं अगली वीडियो में नए टॉपिक के साथ।